Hello students, today we are going to take one step ahead and start simulation of stochastic process. So as you know, simulation of stochastic processes means simulating families of random variables. That essentially means a stochastic process, as you know, is a family of random variables. So in particular, let us start with a simple process called renewal process. In the last few lectures, we have used this renewal process when we have seen a special form of renewal process that is called Poisson process. So let us first recall the definition of a Poisson process in order to understand how to simulate renewal process. Let us first recollect what we have studied when we studied Poisson process. So we have said that a stochastic process nt t greater than or equal to 0 is said to be a Poisson process with rate parameter lambda if it has stationary and independent increments. If it has stationary and independent increments. Now let us try to understand what happens with this. We say this process is a Poisson process if it satisfies these four conditions. Then we defined another notion of a process, Poisson process, by using some different definition. So that definition we will use today to understand what is a renewal process. So this was the definition. In this definition, we said that let Xn be a sequence of non-negative random variables representing the time between the two consecutive arrivals or two consecutive events. So we call this as inter-arrival time, and let that time be defined by Xn. Then we have defined, based on these Xn's, we have defined another random variable, that is Sn, or a family of random variables Sn. For fixed n, it is one random variable. For varying n's, it is Sn n equal to 1 to 2. So it is again a sequence. So this random variable is nothing but it denotes the arrival distributions. Because xi's are inter-arrival, if you sum over them, you will get the arrival distribution. And if you define it in this way, where S0 is equal to 0, then if you define nt to be maximum over n greater than or equal to 0, such that Sn is less than or equal to t, then nt denotes the number of events that have happened in the interval 0 to t. Now when we define Poisson process, we said that if these xi's, if these xn's that we are defining follow exponential distribution with mean 1 by lambda, then we say it's a Poisson process. But if these xn's are any continuous distributions which are non-negative, then we call such a process as renewal process. That is what we mean when we say a renewal process. Okay. Now let us go back to our definition and see how the renewal process is. So our goal is to simulate a renewal process nt t greater than or equal to 0 generated by independent xi's which have inter-arrival distribution f. Okay. So now the process is to generate this particular inter-arrival distributions, and in order after generating these inter-arrival distributions, we may get nt, which is the number of events in the interval 0 to t. So let us try to see a rough algorithm of how to generate this nt. So as we can understand, if I want to simulate a random variable capital NT, okay, so this t is fixed. If I want to simulate a random variable capital NT, what are the things that I need to do under this setup? Somehow I need to understand that capital T is fixed, and in the beginning there will be some small t, the time counter, that starts with 0, and at 0 there is no event that has happened. So n is equal to 0. So we started with t is equal to 0, n is equal to 0. The next immediate question we can ask is, how long will it take for the first event to happen? The answer is the inter-arrival distribution. So the inter-arrival distribution is f. So naturally our job then becomes to simulate X which follows F. Now to simulate this X following F, depending on F, you are free to choose whatever techniques that you have seen in last few lectures. So now assume that you have generated F. Then how to convert it into a process? So once generated F, what does this X will denote? The X will take one value, which is actually a time value. So whatever value of X is generated using simulation, we will take that as a time value. So at that point in time, let us say capital X is equal to small x. So at the point small x in time, one event of this kind has happened. So nt or nx is equal to 1, and the time at which it happened is x. So to allocate that thing, we will set, first we will check if our t plus x, that is the x, and now our capital X is small x. So t plus x, whether it is less than t. If yes, that means this is a valid event and we are going to count the event. So we will take t into account and we will set t is equal to t plus x. Since this event was the first event, the t was 0. So our new t is x, and we have n is equal to 0. So n is equal to n plus 1. That means nt will become 1. Okay. And because t plus x is less than t, we have not yet reached the random variable capital NT. So we will again go back to step 2. Again generate a next random variable x which has distribution f. Again you will check the same condition, t plus x is less than t. If it holds, you will do the same operations. If t plus x is greater than t, that means you have simulated nt, which was the predecessor. That means nt will be equal to n. Suppose t plus x is greater than t, then whatever n you have generated will remain and you will stop the process. That is what will be the value of capital NT. So this is the simplest algorithm to generate a renewal process. In particular, you can generate a Poisson process. We have seen that how to generate a Poisson process using such a random variable. Now, let us understand this thing. The last step in this process can be written in a different manner. So in particular, capital NT can be said that capital NT is minimum over n such that x1 plus x2 plus xn is greater than t. So if you use this definition, then you just have to write simulate capital NT such that this condition is satisfied. But in order to check this condition, inevitably you have to go through this process. So this is one beautiful thing about the simulation of renewal process. This is the simplest algorithm through which you can generate a renewal process. Now a renewal, depending on this f, how difficult it is to simulate, the complications vary. So in particular, this particular method also gives you how to simulate a Poisson random variable. For example, if you set this t to be equal to 1, then and the xi is to be exponential with mean 1 by lambda, right? Then you will get a Poisson lambda random variable. So without setting this t is equal to 1, you will get nt following Poisson lambda t. If you set t is equal to 1, you will get Poisson random variable. So far, I have not given you an example of simulating a Poisson random variable. This is the first time I'm telling. So in using this algorithm, it is very easy to simulate a Poisson random variable with mean parameter lambda. The other methods like inverse function method or rejection method can also be used to simulate Poisson random variables, but this is the most simplest method for simulating Poisson random variable with mean lambda. Now let us focus again back on our Poisson process and let us try to see whether is there any other beautiful method for simulating a Poisson process or not. The answer is there are some beautiful theories developed around Poisson process. and because of which you will be able to see some interesting methods for simulating Poisson process. One of them is this fact, Campbell's theorem. So as I have already mentioned that if you have a Poisson process and if you want to consider the arrival distribution, the joint arrival distribution of this Poisson process, we already know that the inter-arrival distribution has exponential with mean 1 by lambda, and xi's are the random variables that represent the inter-arrival distribution, ith inter-arrival distribution. Okay. Then we have seen that S naught was 0 and Sn is summation over I equal to 1 to n xi. These are the arrival distributions of a Poisson process. Now they share a wonderful relationship given the value of a Poisson process. For example, if I tell you that the number of outcomes in a Poisson process up to time t is n, then these inter-arrival distributions have one beautiful property that is listed as a Campbell theorem, that the joint distribution of these random variables S1, S2, Sn given nt is equal to n is nothing but the distribution of the order statistics of uniform 0t random variables. The joint distribution of the order statistics of uniform 0t random variable. Just to remind you, order statistics means the random variables are arranged in order. Essentially, if you have uniform random variables, let us say ui, then minimum over ui's will denote the first order statistics. After removing that minimum, the second minimum will denote u2, and this continues till un, where un denotes the maximum of u1, u2, un. So this this theorem that or this fact will help us to simulate a Poisson process. How? So let us try to see it through an algorithm. The algorithm is pretty nice and short. Let us say I want to simulate a Poisson process, okay? And I want to simulate NT. So when you simulate a Poisson process, it is not sufficient to simulate only NT, that is the number of arrivals in the interval 0 to t. But you also need to give the inter-arrival times. As you have seen in the first case, we have given those inter-arrival times by setting t plus x. Okay. So instead, if you want to simulate a Poisson random variable, you can straight away simulate the Poisson random variable, and whatever value you get or that Poisson random variable, you set it to be equal to n. So now the condition that nt is equal to n is given to you. So now your job is to simulate the arrival distribution, the joint distribution of the arrivals. How will you simulate? Using Campbell's theorem, you know that the joint distribution of the arrival times is nothing but order statistics of uniform random variables. How many uniform random variables you need to simulate? If nt is equal to n, you need to simulate n arrival time distributions or n random variables which will follow the distribution of arrival times. In particular, in this particular case, you need to simulate n uniform random variables in the interval 0 to t and arrange them in order. That is what will give you the order statistic of the uniform random variables. Okay. So now, once you set nt is equal to n, your job is to generate uniform random numbers u1, u2, un, arrange them in order and multiply them with t. That will suffice for giving you the event time distributions. That's what you will do. And therefore, you were able to successfully generate or simulate a Poisson process, time homogeneous Poisson process with rate parameter lambda. Now in the next video, we will see a generalization of a time homogeneous Poisson process to a time inhomogeneous or a non-homogeneous Poisson process and we will see how to take up the simulation of that particular process so that we will have edge over the simulation process. And it is important to note that All these processes are very common in nature.